Okay, so welcome to the morning session of Big Data 2024. And we're delighted to have our own Tianxi Cai from the Tianxi School of Public Health will tell us about crowdsourcing with the EHR.
Thank you. As you can see from my title, the talk I'll give today will focus primarily on electronic health record data, and we call it EHR. And for some of you, it might be slightly less familiar what EHR is, but I want to tell you that I've been working in the field for the last 20 years. And I used to have this, really nice explanations for why it's so significant, et cetera, because I have to write a lot of NIH grant. And I have this very nicely written slides. So of course, fast forward, ChatGPT came along and I had to chair this session for NIH about, AI research with EHR. And we have the forum about you should think about how we're gonna move forward in terms of research agenda. So I had to sort of as a necessity, I had to ask ChatGPT why EHR research is important for AI research. And I was really shocked how good it is. It literally made me nervous. Why do they need me anymore, right? I felt like I had such an expertise. I worked in 20 years. I know the field very well. Apparently, they learned from our 20 years of research why it's important. So I no longer have my own slide, just cite them. But at high level, basically, it's a very useful data. It has a huge amount of data in terms of both breadth, like what kind of data elements there are, cover basically many aspects of the health, almost entirely if your entire health record is in there. It also is very deep in the sense that many patients, right? All the sick patients are in the hospital. So it's particularly helpful actually to study rare conditions because they are really already in the health center. About 10, 15 years ago, I worked with a group of psychiatrists to try to recruit patients who had bipolar disorder into the study. We were going to genotype them. He has a side-by-side two studies ongoing. One is his typical NIH study. He goes out to try to recruit patients to enter his study. And the other one, we work with him to build an algorithm, identify patients in the record, contact them. You almost don't need to contact in the sense that they will come back, right? And you get the blood, get their consent. So it turns out basically we were able to recruit about 4,500 people in 2 years. And it's bipolar is relatively rare. And they spent 9 years was only 400-something patients. So you can see the sort of the benefit of this kind of data, but I would give you a few specific examples later also to highlight why such data is very useful. But not only EHR data itself is very useful, yet it does have, as I mentioned, many different kind of modalities. So in addition to, for example, EHR codes, essentially for billing purposes or for process purposes, right? Physician will provide a prescription and that would be a code and you can see, oh, the patient is taking this drug, right? So these are, we call a structured data. We also have rich free text data. So every time when I go to see my doctor, I will actually watch her typing notes because I'm curious how she writes it. So these are free text data, document even more detailed information about the visit, signs and symptoms, for example. These are typically not coded. They also have our medical history, or sometimes you have adverse reaction to the drug and you actually don't typically code it. So you have basically additional free text data. That's a huge amount of data that stores in the EHR. We use natural language processing to extract those. And also we have other modality I mentioned, like imaging. If we go to, I was coughing for a long time and they did a CT for my lung, so you'll get CT images. not only we use EHR data for research, we also link additional data sources to the EHR, for example, disease registry. So currently we have 2 ongoing studies actually link disease registry for rheumatoid arthritis and also multiple sclerosis. For both of these 2 conditions, we have routinely collected clinical outcomes. Those are more similar to clinical outcomes that we would collect in clinical trials. So for example, disease activity, that is not something that physician on a day-to-day patient care kind of scenario will collect. So if you link those data with the EHR data, that will enable us to impute the disease activity. So it makes the data even richer. And also, like a VA, Veteran Affairs health system, is a huge health system, right, covering all the veterans, many millions of patients. They also run clinical trials within their health center. So we are currently also linking clinical trial data and at the patient level within the EHR. And there are also many initiatives you might have heard, for example, All of Us. That's actually an effort by the NIH. Earlier days, there will be eMERGE, and also from the UK, there's UK Biobank. So we further allow people to link the biobank, which will give us genomic data that's linked with EHR. So EHR data are collected like longitudinally by nature. I have many years of record in the Brigham system. So you can actually rewind in time and build decision support tools. We have an ongoing project with a group of psychiatrists actually try to develop tools to predict the risk of suicide. Because if we can detect that someone is basically at the verge of doing something, potentially there's some kind of intervention that the clinician can think about, right? Or actually can work with the family members, etc. So we developed a risk prediction tool to highlight, to flag these are the patients at high risk. Actually, our current ongoing clinical trial is not to see like what intervention the patient will, the doctor will give. We just give the information to the physician. They decide what to do with the family, with the patient. And we have a randomized another group of patient doctor, they don't receive the information. We just want to see, does it help for them to know that there's high risk? So in that setting, we actually here, I'm just showing you that we develop an algorithm, like you can see that you can achieve a very high accuracy in differentiating people who might commit suicide in the next few months versus not. Like you see here, like for the outpatient is 0.92, but I do want to remind everybody that absolute risk of suicide is very, very low for the general population. So that's actually not very useful. We're not going to contact everybody to have false alarm. So that's why clinical decision support is so bad. I mean, so hard to develop because you, unfortunately, a lot of time you have to think about the consequence of a false alarm, right? And also the cost burden to the society. So we are actually studying a particular scenario where we are considering the psych ED patient who are already in the emergency department because of the psych condition. So that is much higher risk compared to the general population. Over there, if you see patients who have 5-fold increase of risk, they really have a, more, we actually found that if we take a bucket of top, I forgot what was the top 1% of the exact threshold, their absolute risk was 40%. So that's very high. So for those, we believe that something can be done. So that's basically the kind of like a risk prediction tool that potentially can be used for clinical care. We also have collaborations that really try to draw real-world evidence from the electronic health record data. We did a study with the FDA about 2 years ago where they were worried about pulling some device off market because that device, the first 2 iterations already got pulled off market because they have higher adverse risk. So the company did further refinement and it seems to be okay. but they still see like a little bit sign that potentially, so they had a congressional hearing and before scheduled in November, and they contacted us about like less than a year before and asked us to look into the study. So that was the most challenging study for us to do because you have a hard deadline and the evidence is really, really sort of scary for us to deliver, right? Because what if I made a mistake? But long story short, we were able to look into the data based on Veterans Affairs, and we look at patients who actually went through endovascular aneurysm repair. So it's a device. And we compared the patient who use that particular brand of device versus traditional other subtypes of device. Here on the right hand, the bottom actually is showing you different devices. The blue line is the AFAX S, that's the one that already got pulled off market. The second one also pulled off market. So it's sort of reflecting why they got pulled off the market, because that's an event rate of so-called a type 3 endo leak. So essentially start bleeding. The orange one is the one under consideration. And the dark green one is a traditional device. So you can see that our study ended at 5-year follow-up because the device got off onto the market about 5 years ago. But this is something that I find fascinating, that you actually see a slight increase after after 4 years. But unfortunately, we only had data up at that point. But we were able to basically look into this, and the conclusion from the investigation was that actually they still let the product to be on the market, but to pay close attention to further monitoring. So this is the kind of study I really got really interested because it has a real consequence. I would love to go back and see, because now I have about 7 years of follow-up. And this is also says why we need a huge amount of data, because the event rate itself is fairly low and the patient that went through the procedure is not very large. So you really do need something like the VA, which covers 12 million active patients through the healthcare.
Did the device have a design life, an expectation for how long it should last?
Good question. I don't think so. I don't think they would. They are expected to sort of like, gradually break. But this is also an interesting, sort of statistically speaking, an interesting study that like when the device is first implanted, there's an immediate risk of having this endo leak. And then if you survive the first couple months, means the procedure went pretty well. Basically, it worked well for the patient. Then it's a more longer risk. So from statistical analysis, my research in the early years was in survival analysis. We run a lot of Cox proportional hazards model. This is where it will fail. So we actually specifically look into short-term risk and long-term risk separately for the devices. So of course, you can look into using EHR as a resource to learn clinical representations of many different conditions and further link with more like a biology-driven data sources. For example, we looked into chemical structures of drugs to understand what kind of drugs that are supposed to work and also for a certain indication or potentially have side effect. So this is probably one of the most popular line of work that so-called AI research people are really interested in. You don't need to be perfect here. You are basically rank ordering, right? What has more potential for, if you think about drug discovery, it can greatly increase the potential, the efficiency of drug design. And we certainly hope that will bring down the cost of the drugs on the market. It's not because the drug itself costs so much, right? You have to think about how many need to fail for us to get the one that succeed. So this is definitely something very promising. I have to admit that I know so little biology, is that's all I'm gonna say about. But these are also rosy pictures of why EHR data is very useful for research. But there's a lot of problems with EHR. Today, I will only focus on two specific aspects. So one is that the algorithm that we train on one system often cannot be transported well to another system. There are many reasons for them to fail. One obvious reason is that, for example, if I'm looking at VA as a health system, vast majority of veterans are male. They tend to be older. They tend to have more comorbidity, and their knowledge that you draw cannot be easily translated to a different health system. And for example, if you look at Mass General Brigham, they are very good hospital system, right? They tend to actually receive much sicker patient compared to a general hospital. So their outcomes also not necessarily representative. So basically that's our more of at the level of heterogeneity. Of course, there's also a lot of so-called like a distributional shift in addition to like patient characteristic, their distribution of their baseline like characteristic differ. It could be like the way that, you know, the physician treats the patient might be very different. So those differences also make the model themselves not transportable. And another issue that I will touch upon on the second part of my talk is actually the heterogeneity in terms of the coding practices. So basically one code, for example, in the MGB, they might have their so-called local code. You have to often, like when we do a lot of this so-called federated learning with many health centers, oftentimes I have like manually work with the local health IT to figure out what's a corresponding code. So that is a very, very painful and error prone. So we are also hoping to produce both the knowledge and the algorithm to make that step more efficient. So I'll focus first on the problem of generalizability. Basically, you have many health centers, right? You can work with multiple health systems. And our goal is to draw so-called reliable evidence. Like there are many ways for us to think about generalizability and reliability, right? So in order to improve the reliability, one way is that, you know, basically crowdsourcing. You have many health centers, right? We do acknowledge there's some kind of heterogeneity. One way to think about it, you basically have to impose some prior assumption about what kind of heterogeneity that you are expecting. So one way to think about it is that maybe some sites are more similar to each other and some are not, or you have a target population that you are interested in and you want to identify all the sites are more similar or more transferable to my target population. While you at the same time allow for heterogeneity across sites. And also, because we're working with health system, another thing you have to pay extra attention is that we can never share patient level data. So the individual level data, because of the privacy concerns, have to mostly stay behind the firewall of the hospital. So that's why we focus along so-called federated learning, where we only allow sites to share summary level data, like a covariance matrix, for example, a mean vector or beta coefficient, etc. So we definitely aim to develop algorithms that only require the summary level data sharing. In terms of robustness, we are interested in developing so-called consensus learning, essentially draw inference from the group of sites to figure out what's a majority that provides me a reliable evidence. We also consider distributional shift, as I mentioned, you know, from the if you have a target population and all the sites, some of the sites may not be similar or their knowledge not transferable to the target population. How can you figure that? How can you actually synthesize all the information to optimize the potential generalizability? So let me just give you like a brief summary of one aspect that we looked at. I'll focus more on the distributional robust aspect. So just imagine that you have L source population, you have L sites, and you want to infer about some parameter theta. So let's say that you're looking at, you know, the effect of this treatment on the drug, right? That's the parameter you are interested in, like causal effect. And or you have a regression model, right? This is even simpler, like a linear regression. You have theta to index the effect of those covariates on Y. And we are interested in identifying those shared parameters. So let's say that, the index set, like for any given theta, the potential target parameter, the set V is basically how many sites that actually agree with that theta, right? And if we want to come up with a way to do so-called consensus learning, of course, you have to impose some assumption, right? So let's say that for now, you are comfortable with the assumption that majority of the sites agree with each other. So then there must exist a so-called prevailing model. So this theta star, there exists such a theta star, such that more than half of the site will agree with that particular theta star, although we don't know what theta star is.
When you write theta I equals theta, this is an RD, like close to, or
this one? This is exactly equal. So that's a population parameter. So we are saying that which of the sites whose population parameter is equal to that theta.
Why would different models in RD ever be really equal?
That's a very good question. In the more realistic scenario, for example, that's why like in meta-analysis, when we have many sites, we'll say some of the sites are more within a small, boundary to each other. We are indeed working on that, but this problem itself is hard enough that actually, because when you have a subset that do agree with each other, okay, exactly, you still have this remaining site. You don't know how far is far, right? So in that kind of situation, actually, to make inference about this data stuff is very hard. Because if they're very far apart, it's very easy. You basically have so-called perfect separation. You can draw a line, they perfect separate. So in that sense, like statistically speaking, from the inference perspective, there's no penalty to pay. You can identify that separation with probability going to 1, and you can draw inference as if you know what the majority sites are. But that's usually not the reality. Reality is that they're in between. Some are here and they're not the heterogeneous site. So I used to joke that my students, when they make mistakes, I expect them to make all kinds of mistakes. When the mistakes are the same, I think they copy each other. So, so when they're heterogeneous, you actually don't know where they are, right? So in that case, actually, and also sometimes they're very close, but not exactly the same. So when you draw inference, then you have to pay the penalty of figuring out which set that actually belong, basically define this consensus set. And in that case, basically it becomes a post-selection inference. You have to, it's no longer a regular inference. So we actually wrote a paper with Stan Guo from Rutgers and one of my former postdocs who just went to Berkeley, where we consider so-called robust inference for federated meta-learning, where the key is really to, we have a voting matrix to figure out who potentially belong to the majority, and you actually use resampling to figure out what are the potential majority sites, and you actually, in the end, almost have to pay that uncertainty by taking a union of the possibilities. But of course, when you take a union, you can always take a union so large that you always guarantee the coverage. But at the same time, of course, you want to guarantee to make sure the length of the confidence interval is not too wide. So the only thing we can guarantee in that kind of scenario in terms of optimality is that when you do have separation, we can show that's the best you can do. So basically, our inference will agree with what you would have done had you know what the site is. But I won't dive deeper into this particular problem. I'm more interested in the second set of scenario where we have a target population. For example, let's say it could be, a combination of the source populations or just one new population that you're interested in. You have L source population, you have a new target population, and you want to transfer knowledge for this new target population. But so most of the transfer learning literature consider the scenario like what I described before. which ones are similar to that one, I'm going to transfer. But what if the new source, the target population is different for any existing population? So the motivating example that I will show you later actually focus on genetic risk prediction model for patients with mixed race. Most of the existing literature focus on like you have European descent, they have a polygenic risk score. And recently we have a lot of push for, addressing for heterogeneity and minority population. So you'll see that we just published a paper with the large VA group in Science. That's the first time we have such a large amount of genomic data for African American. So we are able to potentially construct genetic risk score for African descent, but we never have enough power. What about the mix, like a white and black mix, white and Asian mix, et cetera, et cetera. So for a mixture population, for that case, they're different from any of the potential source population we can construct with reasonable sample size. So that is a kind of scenario that you have a target population that differs from everybody. How can we potentially actually leverage the multiple source population to make inference? So mathematically speaking, you can look at this by, X. L is the L source population of the covariate has its distribution. We don't assume they to share at all across population. And Y is the outcome, and Y given X has its own distribution. You can see again index with the superscript L, and your target population has its own distribution for X indexed by Q, and then the Y given X, the conditional distribution indexed by Q of Y given X. So you of course have to make some assumption, right? The transferability. So that, as I mentioned, the standard transfer learning assumption assumes that the conditional mean distribution of Y given X is close to the target population, at least for some of them, right? That's a standard transfer learning. But here we are considering a slightly more general scenario considering source mixing. We assume that the target population can be approximated by a mixture of the source population. So in that case, basically, we write this Q as a linear combination of the L source population distributions for the conditional mean. And that kind of scenario actually have been very popular in recent years. So you might have heard a lot about so-called distributional robust optimization. And in this case, actually, they consider this as a group distributional robust or group DRO. So what they are trying to study in the current literature for this kind of source mixing population, they focus a lot on so-called generalizability. So what they consider is that they don't actually know which target population you're interested in. They are thinking, okay, you have a future population. That could be some combination of the source population, but I don't know which one. So they are protecting the worst case scenario. They want to guarantee that the worst case, the minimum gain from your model should be maximized. So that they call it a minimax. Or max mean. They actually call it max mean. I don't know why they don't use our more commonly used the minimax. Minimize the maximum loss or maximize the minimum gain. So this actually is a very interesting scenario because they actually consider the so-called adversarial attack. So in the future, you don't know where the attacks come from. So they consider this kind of potential uncertainty set, and they want to minimize the maximum loss, for example. In the linear case, there has been two very nice papers, the so-called the max mean estimator, where again, like if it's a linear regression for Y given X, both for the source populations and future target population. So instead of distribution mixing, they're considering the beta coefficient are potential mixture of each other for the target population. And the max mean estimator by Manhilson and Brigham in 2015, and Zhejian Guo wrote a paper on the inference of that. So basically, here I want you to look at like how they exactly define the loss. So when you build a prediction model with a beta coefficient, you have a mean square error, right? How accurate is the model? So what they consider is that they are minimizing, the minimum gain in reducing the prediction error. So the prediction error of the non-model, I know nothing at plug and zero versus beta coefficient that you construct. So that's basically the reduction in the prediction error. They want to make sure that the reduction in prediction error for the worst case is maximized. So it turns out that this has a very nice near closed form solution. The solution of the optimal beta is indeed, of course, a linear combination of the L beta coefficients. And the minimization has a nice geometrical interpretation. So you can think of these, dots are from the L source site. So you draw a convex hull. It's the closest point towards zero because they are making sure that your gain over zero is optimized. So in sort of, if you have a one dimension, it's actually naturally a very good prior guess. So particularly in high dimension. In high dimensional regression, right, we always shrink towards zero because we think that, if the signal tends to be sparse, so zero will be a good prior. In this case, it's almost similar. So basically, when you see a lot of beta from different sides, they disagree with each other, but all over the place, they will pull it closer to zero, so it will cross zero. So actually, it will also give you a sparse solution in that case. But our case is a little bit different. When I first heard about the work was actually from Zijian, and my first question to him that why do I have to care about all the potential adversarial attack? I actually have a target population. And what I want is at least around the target population, you do well. That way, we can overcome one major limitation of this kind of distributional robust estimator, very conservative. So it can do very poorly for one particular beta. That's a price to pay, right? In order to be very robust, you could also do very poorly because their so-called uncertainty set is too big. So in our case, we actually consider the scenario, I do have a target population, but my goal is also to improve the robustness in the sense that in the future, I will allow any target population that's kind of similar to my current target population, you have to do well. So your goal is also not to only optimize for that particular target population, but we usually for new target population, we have very limited data. So we are assuming that you only have very, very small amounts of so-called label data. That way you can actually leverage the source data to help you. And with that in mind, we came up with a much more sort of constrained, a smaller constraint set that I don't consider all linear combinations. I only consider linear combinations or the betas that don't do poorly for my target population. I do have some label on the target population, right? So I know if I, for example, just do supervised training, use half of the data, I can test how good is my model trained with my target population. And here, basically, we want to not do much worse than that particular supervised training. So target only training, basically. And also remember that early on, we want to achieve the maximum gain over a null model, right? In their case, the null model is zero, but I do have a target population. Why do I want to use zero as a benchmark? So we actually allow the model to consider any initial estimator, could be your target only initial estimator, or could be some kind of source mixing initial estimator. So at the end of the day, we show that we actually came up with the so-called guided adversarial robust transfer. So our estimator is also a linear combination of the source estimators, but also including the target only estimator. And here we have, as I mentioned earlier, we have a slightly smaller constraint set, and you also can solve the problem relatively easily. But I do want to point out that there are many parameters you don't know in this estimator, and you always have to estimate. So basically, you can construct plug-in estimates. I'm going to skip some of the details. The only thing I want to point out is that because we do have the target-only estimator, but we want to enable the prediction to do well for future populations. So we do have to do a lot of sample splitting to make sure that we don't get constrained by the limited sample size. And here's a brief summary of what are the theoretical guarantees that we can achieve. So it is indeed the so-called distributional robust. So we are basically showing the optimality within a constraint set that contains a distribution around the target population. We do show that as long as the initial estimator, if you choose the initial estimator, for example, as the target-only estimator, it will pull towards the target-only estimator. And as I mentioned earlier, we say that you construct basically a constraint set near the target population. So you as a user have to decide, right, what kind of robustness you want to achieve. If you want to be very close, then you are really optimizing just for the target population. But you can make it bigger because you want robustness a little bit bigger. So our parameter tau actually indexes the user choice. But basically the robustness is also depending on the choice that you make in terms of how large the population is. But what the nice thing that we can achieve is that we, depending on, like I said, what is the parameter tau that you want to set. But we can show that if the so-called source mixing assumption is correct, in a sense, my target population actually can be approximated by the mixing of the source population, then we can estimate the target parameter much better than using target. That makes sense, right? I can use a lot of the source distribution to estimate the target, but we also have not much to lose in the sense that in case that's wrong, I will still be able to recover the target parameter if it's very wrong, if it's basically depending on the tuning parameter. I just want to quickly show you the example that we looked into is look at the HDL. It's basically the protective part of our cholesterol, and HDL is associated, like higher HDL is associated with lower risk of cardiovascular disease, but the protectiveness of HDL actually varies greatly across race. Asian population tend to have higher HDL, and the African descent, even though they might have higher HDL, it doesn't protect their cardiovascular risk as much as other populations. So there's a lot of interest in understanding the genetic component of HDL. And we used UK Biobank data and separated that into different training cohorts. And the target population, as I mentioned, is the mixture population. And under UKB, they actually clearly say this is a white black, this is a white Asian, etc. So we use the white black population as our target population. But because I'm interested in the generalizability, so I also want to see how well my genetic risk score trained aiming to perform well for the white black population, how well can that perform in a different population? So here, the interesting thing is that the one on the top shows you like how much weight different methods put on for each of the source. So the first one is the blue one, just target only. Target population, of course, you should put some weight on the target because you're estimating for the target. And our method on the top also put weight almost half on the white and half on the black. So it kind of knows that it's a mixture population. I'm learning from both. So here from, this is actually mean square error reduction compared to the target only model. So basically you do much, much better compared to target only. And here is like we achieve, for example, 60%, 65% of reduction, whereas like other methods basically can do much worse. And this, I just want to mention, these are the traditional transfer learning method. They can do much worse compared to ours. But this is even more interesting when I look at outside the so-called generalizability. This is a completely different population. That's Mass General Brigham biobank. And they have a self-reported race. Sometimes it's white, black, etc. And sometimes they just say other. So this is basically a mixed bag of different patients. And then you can see that we can still do much better than the target only, but all the other methods actually did even worse compared to that. So that's sort of highlighting the so-called generalizability. So the last component I want to talk about is transportability. So far I'm focusing more on the distributional shift, right? Both in terms of covariate distribution and the conditional distribution. But here, when I work with multiple healthcare centers, they are different in many other ways that got me started working in this problem. I was actually dragged into working on EHR data about 20 years ago. And I was interested because I'm interested in so-called precision medicine, like risk prediction, conditional, like causal modeling to infer who can be treated by what. But then quickly I found out the data is so messy that 20 years later, I still work with the data. I actually now spend much of my team work on the data. We even come up with tools to harmonize the data, as I want to tell you here. So basically, when we first went to the VA, that was about 8 years ago. And at that time, we already started working on automated data harmonization. We have small algorithm. We thought, great, this is my test case. And when I went to the VA, they told me they have 400,000 lab codes. I quickly decided I'm not going to do that. 400,000. Do you know how many labs the BI, the Beth Israel, has after they manually curate? 200. So in other words, the 400,000, most of them are actually the same lab, because the reason they have so many, VA has many hospitals. Each of the hospital with many work with many local clinic or wherever to do their lab testing. It all came back with their own unique ID. So then there's a lot of human effort in harmonizing. Like even CRP alone has hundreds of codes. And medications, that's also usually my horror. Like I already finished my causal modeling paper. I'm about to send out. And then we checked, we realized that we missed a lot of the medication because the medication is coded as a procedure if it's a transfusion. So if it's a tablet, it'll just be like a typical so-called axonome code, a medication code. But if it's a transfusion, they don't code it as a medication. They code it as a procedure. And we didn't know. So that's when I started getting interested in this, because I spend so much time, I have to redo everything. And even though we can do a lot of manual mapping, and that's usually what we do when we have this so-called consortium to do federated learning, because we don't know their data enough to do automation. But in recent years, especially with the large language model, there has been a huge amount of interest in trying to see, can we actually represent the meaning of a code? So that's why we call it representation learning. But sort of mathematically speaking, they just come up with a numerical vector to index the meaning of the code. And that vector, like similarity between two vectors, will tell you how similar or related two terms or two codes are. So if you write down as from the code translation or data harmonization perspective, like you write down encodes from one system, encodes from the other system, you line them up and you want to map them. Basically, a code at a VA, what can it be mapped to? But of course, there's a lot of complications here. For example, VA has 400,000, and let's say VA has 200. Obviously, it's not one-to-one, right? It's many-to-many kind of mapping. But if you can imagine that if the codes are all lined up as indexed by the semantic embedding vector, so that's a representation that I meant, the embedding vectors, so that becomes data to us now, right? Because that's what you're just looking at a bunch of strings, like how do we map? so that the representation learning basically turn those words into a numeric vector. Then you can train all kinds of algorithms to map the codes. So the early days back in 2013, that's when I first got interested in this. That was like before all the fancy models came out, transformer, etc. So that basically the word-to-vec model was the earlier paper that tell us why like this kind of semantic representation makes sense. So that's their typical example. Like if you take the vector of king minus a vector of man plus the vector of woman, it's very close to queen. So that kind of give us intuitively that actually makes sense. They also showed that you can, look at a bunch of vectors in English, a bunch of vectors in Spanish, and you can also see that they can actually do a transformation that they can be aligned. So that means that we can actually translate, right, for language. But many years have passed since that time. We know a lot more about how we can represent meaning of text. But what we observe is more than just a text string, right? What we observe is actually how the codes are used in electronic health record data. So basically, when a doctor sees a patient with this condition, they tend to give them this medication, this lab is measured, this procedure is given. So there's a lot of information that's actually embedded in the electronic health record can teach us the meaning of a code. It turns out EHR is amazing in doing this. You can use word-to-vec and do a simple matrix operation to train a vector can do extremely well. So in other words, you do have additional information other than the language itself. But of course, I also don't want to throw away the language, right? Because if you check whether we do a good job, you're actually staring at the string. Because you don't know what that means in the health sector, like you and I are not doctors. So in that case, that means that the text string itself contains a huge amount of information. So we want to basically leverage the both sides of the world. But another information that we can learn in the literature is a relational databases. So there's a unified medical language system that's curated by NIH. Actually, it was a human curation for decades. And over there, like you can go in and check, type in a string. It will tell you what is the concept and find all the synonyms of the concept. It also tell you which one is a broader concept, which one is a related concept, like may treat, may cause, many different kinds of relationship. So that's like human knowledge, right? They actually manually curated, although there's a huge amount of error in it. Suchi sitting there probably can tell you with a lot of emotions how bad the data is. But on the other hand, it's still very valuable. It's largely correct. If you just think of proportion-wise, it's still very high. So in other words, you can almost think of that as a noisy label. And now also we have GPT-4. Like instead of me staring at it, throwing to GPT and say, hey, tell me which ones are correct. So you can also ask GPT-4 to further correct. So in other words, you have EHR data, you have text string from pre-trained language model that you can represent. You have knowledge bases that you can pull. You have GPT-4 can further curate so-called silver standard label. So we basically assemble all of them and throw into like overall kind of training data. So as I mentioned, we have EHR data and we only use summary level data. This is actually super simple. We just look at co-occurrence counts, how many times the codes co-occur across different time window. We collected data from 7 health centers. This is one of the hardest studies I've ever done. I started this, I would say almost 7 years ago. Like if I didn't have tenure, I wouldn't do this. My postdoc went to Bordeaux, but he loved it. He spent a month sitting with them because they're like a really interesting working with us, but there's so much hurdle. So it took us 7 years to finally have the data that I can show you today. So you can see the amount of data that we use to curate like the summary level data. Like Mass General Brigham have 2.5 million, VA we used 12.4 million, and Bordeaux also has like 2 million, etc. But you can see these are different types of code that they have. And these are the columns that non-standardized code. So that's all represented different kind of local code. So you can see the huge amount of, and also other, like we don't even know what they are, but they are local codes. So you can see the total number of codes is humongous as well. So we use both the textual description. So the co-occurrence matrix give us one kind of initial embedding representation. So we can think of it like the meaning of the code from the healthcare perspective. And then text string will be each of the code has a string attached to it, right? Your dictionary. So that you can use pre-trained language model. But here they are actually in French for the Bordeaux hospital. We did just simply use a translation into English and embed them. We also use like a knowledge graph, as I mentioned earlier. So here, just high level, in terms of the algorithm perspective, we use a graphical attention network. So we basically look at it from the network perspective. If you're a node, I need to learn like what are the links that connected to this node. The attention network, basically not all the nodes next to me are equally important. I also want to learn the attention. Essentially, fancy way of saying weights or coefficient. But basically you use a neighbor to help to predict the meaning of the code, right? That's how we learn the context, right? Here, the trained embeddings, we evaluate in many ways. So in addition to mapping codes, the representation actually helps us to do a lot of downstream tasks, which I will show you. But here is the first task, like if the semantic vectors are good, then like the two codes that are similar to each other, you expect their cosine similarity of the two vectors to be close to each other. So that's the AUC here. Ours is basically on the last column, and these are the OpenAI, like you can use GPT-4, go to their website and download, like you can request, but they'll charge you to download. But we did do that for just as a comparison. So you can see that our embedding attain very similar or even slightly better performance sometimes compared to the OpenAI algorithm. That's my personal explanation really is that we use a lot of the EHR data that they are not trained with. And here is like a detecting relatedness, like a drug and medication will be related. They are not similar, right? Relatedness is a lot harder. And you can see we can do substantially better compared to the OpenAI algorithms. And here is the accuracy of mapping, local code mapping. So the VA, they actually also manually curated a lot of the mappings. So the LOINC is a standardized terminology, and we map to a local code to LOINC. So you can see that you can view our embedding almost like a smart search, right? If someone comes here to search for a local lab, search for a particular lab, they'll pop up. These are the codes that you should use, right? These, by the way, these are completely untrained, completely unsupervised. Even though in the training of the knowledge graph embedding, I do put in these similarity links, but it wasn't specifically trained to do this particular task. But in order to learn the meaning, you should know, right, what codes are similar. So this is definitely very encouraging. And here's something I'm most excited about. So from the representation, basically, you can then go back to individual level patient data. If you take, so in this study as a proof of concept, we looked at patients who were first diagnosed with Alzheimer's disease. Say they receive an Alzheimer's disease code. Then we looked at 2 years leading up to that code, that date. And within that 2 years, we look at what happened to the patient. And we can use basically the embedding to represent the meaning of each code, right? You have simple ways to aggregate all the embedding together. All we did is a so-called TF-IDF. We add up like how many codes you have and multiply the counts with my embedding, but we weighted by like how much, how important each additional concept is for AD, because I'm only interested in the related concepts. So that gives us a patient representation. So we take 2 years worth of data and we represent the patient. And then we have data from UPMC, University of Pittsburgh Medical Center. We have data from Mass General Brigham. We actually user embedding representation co-train the cluster. So these two clusters actually correspond to each other. And this is really just showing us the risk to nursing home admission. So from that date that they first get AD, we look forward to see who are the patients who quickly will be sent to nursing home, who did reasonably well. But these all have Alzheimer's disease, so their risk of going to nursing home generally high. But you can see that the cluster 2 is much, much higher risk compared to cluster 1. But to me, the most interesting thing is that I am finally able to jointly cluster 2 without me manually trying to harmonize the data, because I do not care what code each of the institutions have. I use a representation. That way, for example, let's say that you have BMI greater than 35 from one institution as obesity, but you have another like extreme obese, another institution is not based on BMI, they just have a code of extreme obese, in which case the two embedding vector themselves should be very close. So to me, I don't care anymore exactly what they mean. And that is sort of encouraging that we are able to actually show that you can see fairly reasonable consistency across the institution. So let me just wrap up to say that hopefully I convince you that the real-world EHR data has a lot of potential for this kind of translational research to improve healthcare. We do believe that integrating multi-institutional data can help us to further improve the value of EHR data, reliability of the evidence. But there's a lot more problems with EHR that I did not talk about, the quality of the data. And I think as a statistician, I really feel much more comfortable to know uncertainty. So the knowledge graph that we showed you earlier, for example, we did notice that if you just train using the traditional so-called graphical neural network, it tends to lose ability to know uncertainty. Like all the nodes are like either they're very important or they're not important. So for us, like the level importance, right? The level uncertainty, that is something I think we should keep in mind, like how confident we are. And the reason we're also very interested in knowledge graph is to really mitigate the so-called hallucination. I'm focusing on things I feel comfortable with. I know that they're important before I actually try to draw a conclusion. And as I mentioned earlier, like after struggling with data quality for so many years, I start to believe there is actually science of data, not, as a data scientist, not just like draw the evidence itself. How can we actually make data better to draw more reliable evidence? Thank you.